Okay, so I'd like to confirm, is it any better?
It's better
Okay.
now.
Yeah, you know.
Okay, cool. Okay, solid. So as I was saying, so our speaker is a data camp certified instructor, and he also is interested in bioinformatics. He's also a researcher, and he'll be giving us a talk on introduction to AI and LLMs. Mr. Gama, the floor is yours, and yeah, we're excited to hear what you have to say.
Okay, thank you so much. I'm also excited to be here. Sorry guys, I might not be turning on my video, so I don't I hope you guys will be okay with that. Am I audible?
Yeah, you are. Yeah, you are. It's cool.
Okay, great. Yeah. So let's get started. I hope you guys are excited, and I I hope you get the very best from today's class. So, as I'm going through, probably maybe when I'm presenting, if any questions come on, and you guys can, Ebuka, Sai, and then if you guys can do justice to it, you can just go ahead and do it. Not, or if you can just be keeping track of the questions when it's Q&A time, I can work on that. How that works.
It does. It does.
Okay, great. So let me start sharing. Uh, Okay, confirm if you guys can see my screen.
Yes, yes, we can.
Yes.
Okay, great, perfect. Okay, so let's start. So today I'm going to be taking you guys through the origins. We're going to be going back to the basis and then understand what um, how large language models came into being, or what models are, and then how we got to the LLMs that we are having now. So I think I've been introduced to you guys already. So my name is Richard Kama, and then I'm a data camp certified data science associate. I'm also an instructor here for NSK.ai Bootcamp, and you can connect with me on LinkedIn. Just scan this QR code, and then we can get connected. So our agenda today, we're going to be looking at the fundamentals of AI models, what AI models are, the types of AI models that we have, and we also look at tokens and then tokenization, which is the heart of all LLMs. We would talk about that. Then we also look at neural networks and how they were modeled to they were designed to model the human brain. And then we also talk about transformer models, the ones that form the base of all the LLMs that we have presently. So these are the things that we're going to be looking at today. So let's start with our first agenda. I honestly like my classes to be interactive, so I would be asking questions, and then you guys should try and follow up. Um, you can be putting there. If I ask questions and then you know the answer, you can just put it in the chat. The other panelists would keep track of that for me. So let's talk about AI models. But before I dive deeper and then we talk about what AI models is, I just want you guys to just do a quick Google search. Just type model or AI model, and then in Google, in your Google search bar, and then when you go to the image section, just look through the images that you are going to be seeing there. Probably, I'm sure you might see a lady there or some guys, or yeah, those models there. That I did that search and I saw those things and I was laughing in my head. Um, are those female, those male, are they models? Are they AI models? So we need to understand what AI models are before we start, because we are in a RAG boot camp. We need to be able to understand what models, with the role that models play as we go along into the deeper seas of RAG. So models, that is AI models, not the other models that the ladies and then the guys. According to IBM, which I have the link here. When this is shared with you guys, I'm pretty sure you guys might be able to access this. It's just a program that this program is mostly trained on a data, and then with this model is this program is trained on the data to be able to recognize some patterns that are inside that data, and then from that patterns it's able to make some decisions for humans to be able to intervene. So let me give you guys this example. I am going to pen. So let's look at this. I bet if I write this, you guys will know that this is 2, right? This is 2. Okay, so if I also write something like this, you guys will tell me that this is 2. If I also should write something like this is also 2. If I should also write something like this or something like this is also 2. If I should also write something like this, probably we would say this is 2 because we are talking about numbers. So how are we able to recognize this pattern? So these things, this 2 here, this 2 here, this 2, this is also 2, this also 2, this also 2. These are patterns. Now we humans are able to know these patterns, or you guys, we are able to recognize these patterns because we've been exposed to these values. We've come across these values before. We've seen these kind of patterns to be able to know that, okay, 2 looks like this. So if I should start doing something like this, you guys would perhaps be able to tell me that, okay, I want to draw a 2. So all I need to do is just add this pattern and this becomes a 2. Or, sometimes if I do something like this, you know that this is not 2, this is not 2. So you guys know that you guys are able to recognize that this is not 2. So this is a question mark. The reason why we are able to recognize this is because we've come across this plenty data, and then we are able to make decisions from there. We are able to learn from the patterns. That is how AI models are. So congratulations, guys. Humans are also AI models. I don't know. Is it okay? I don't know if the joke is funny, but let's just move on. So humans are able to recognize it. This is how AI models are. So you have a program, and then you have this model, and then you give it you have this algorithm, you give it a bunch of data, you train it, and then it's able to recognize patterns that are inside that data. And that is the most important thing. So models mostly learn patterns from the data. So that is the important aspect that I want you guys to take out of this. So now that we know what AI models are, um, let's look at the next thing, which is the type of AI models, what AI models can do. So one, AI models can process image data. So here you have a model, and then maybe a CNN model, you give it an image data, and then it's able to learn patterns that are inside that data. So you give it a bunch of cats, and then you give it a bunch of dog images, and then you now ask it to be able to now classify which of these images are cats or which of these images are dogs. So that is what AI models can do. We also have models that can also process that you give it maybe an MRI data, that is maybe a brain scan or maybe a skin cancer scan, and then it's able to recognize patterns from that. Then AI models can also process text. So this is mostly our large language models. So you give it a bunch of text, it's able to learn to learn the nuances that are inside that text. And then from learning those nuances, it's able to probably generate a text for you or translate a language for you. So that is what AI models can do. They can also these days we have AI models that can also generate videos. I think we have Sora, we have more. I think Midjourney also have a video generation model now. So there are more of them. And then we also have AI models that we can use them for to do forecasting. So stock price prediction. Okay, so you want to predict stock price. You want to forecast rainfall for over a given period of time. So AI models can do that. So this is what AI models can do. Now, what are the types of AI models that we have? So we have language models. These mostly the LLMs that we have, so the large language models. And then what these models do, these language models, is that they are able to process, you give them a text data, they are able to process that text data and then give you a text output. So for instance, you have text generation models. We also have like language translation models. We have machine translation models. All of these are language models. Then we have image models and then what vision models. So or image and vision models. So what they do is that you give them a bunch of images, they're able to learn from that images, and then they give you an output. Or we have the video ones that, like the Sora that I talked about, they are trained on a huge amount of video. Then you give it a prompt and it's able to give you some video from the prompt that you've given to it. So these image models could be facial recognition models or image generation or maybe image classification models or video generation models. So that is the image or the vision models. We also have audio models. So they process and input, they process and then they output image data. I'm sorry, audio data. So like those of you who have voice recognition, Siri and then Alexa and the rest, you are able to give it a command and it's able to process that command. So using your voice, that is the audio that you give to it. So these are also AI models. Then the last part is the multimodal models. So these ones mostly they can put all of these ones that we talked about together. So they process text, they can process audio, they can process images and the rest. So mostly speech to text recognition models are examples here. So um, you you speak something and then it's able to now translate what you are saying into words. Or sometimes some of these large language models that we have, you give it a text prompt and it's able to process that text prompt to give you an image or to give you an audio or to give you anything. So most of our LLMs these days are mostly multimodal models. So these are the types of AI models that we have and that we can talk about. Then the next thing that we would have to understand is that we are talking about AI models, but and then we are doing um, RAG bootcamp. So why do we need AI models in a RAG bootcamp? So I want you guys to understand that in the implementation of RAG, we need these embedding models, and then we need a large language model. So a large, that is this and LLMs. These are all models that we need. Now, when you understand that, you understanding models will help you to be able to know how to make use of these in your RAG application. So embedding models, mostly what they are mostly used to do is that they are mostly used for vectorization. So you are going to um, vectorization. Okay. So you are going to be having a text. So you have maybe a PDF, and then this PDF is all about text. Now you do chunking, which we will talk about, and all of those things. So those chunks are tokens, which we also talk about. Now these tokens need to be converted into numbers. I don't know. Okay. Let me skip this. I oh my. Okay. Am I breaking?
No, you're doing fine. You're doing fine. You're
Yeah,
doing
we
fine.
can hear you. We can hear you.
Oh, someone
Okay.
says, um, So I think it has to be the person's network.
Okay,
So,
so should
but
I continue?
yeah, go ahead. Go ahead. Go ahead.
Okay. Um. Okay. I just. Okay. So let's keep moving on. Okay. Yeah. Let's go. Let's go. Let's go. I guess the okay. Okay. So let's move on to this. So we're here. So let me continue with this. I don't know if you guys are cool.
Yeah, we can
Please, can
see.
we move on? Okay.
Yeah,
Good.
yeah.
So let's. So here. Um. So we were here. So we need the embedding models, and then we need the large language models. So I was talking about vectorization. So we have these tokens, which I'll talk about. Then we now convert these tokens to numerical representations. So we need a model to be able to help us to do that. Now, when we now store these vectors in a vector store, which is this here in a vector store, we need to be able to retrieve those documents, to be able to prompt or to be able to ask our questions. Um, so that is the reason why we need models to be able to do that. And then models also work in large language models. That is in LLM models. What happens is that LLM models have knowledge integration, and then they are mostly fluent in response generation. So we use these models to be able to generate your responses, to be able to give you a context and to be able to understand the prompt that you've sent to them, and then they will now give you the results that you need from your own data, which is the RAG that we are talking about. So this is um why we need AI models. Or yeah, this is why we need to understand AI models as we are working in RAG. So yeah, let me pause here and ask you guys from on a scale of 1 to 5, how much are you following, and then how much do you understand AI models now? So let me skip this and then check some comments quickly before we move on. On a scale of 1 to 5, um, just give me something. Let me know if you guys are following before we move on to talk about tokenization. I will say 3. Okay, that's cool. Okay, 3 out of 5, no problem. Okay, cool. So anything you don't understand, just put it inside the chat box. I would address them. Okay, thank you guys. So let's move on to the next thing, which is tokenization. So tokenization, what do we what is really about tokenization? So a token is just a single unit of text. What do we mean by this? Um, I don't know, those of you who come from the computer science background. Okay, let me use myself as an example. When I was going to the university, I was told that computers speak in zeros and ones. So if you don't, if when you get to the university, you have to learn that language. So that was the mindset I was having, that I was going to learn how computers speak language. And then I got to understand that yes, everything that computers do is mostly zeros and ones. So computers speak in numbers. So we humans, we speak in English or in French or in whichever way, in whichever language that we speak in. Now, these languages that we speak are mostly words. So we need the computer to be able to understand our words. So we need to now, for the computer to be able to understand our words, we need to now do what we call tokenization. So we now break our words down. So here we are breaking the words that we have. So here we love NLP. So we now break those words down into we as one token, love as another token, and then NLP as what another token, and then the exclamation mark also as what another token. So these pieces of text, these units of text is what we call what a token. Or this could also be a character. So for instance, if you have a a long word, like let's say happy on happiness, here, what this can do is that it's going to break this down into on, then we have happy, and then we also have ness. Mostly these are like some words that are mostly common. So on, then happy, then the ness is also a set of words that can be broken down. So this is mostly I will talk about this, which is mostly the subword division, or instead of breaking it into these subwords, it will mostly divide them into individual characters. So on, that is you, will become a character on its own, N will become a character, H will become a character, and that is how this goes. So this mostly helps computers to be able to interpret our language into a manageable pieces for them to be able to understand. So that is mostly what um, tokens are. Then the process of we now creating these tokens is what we call tokenization. So the process of we being able to now split our spoken language, our words into individual tokens is what we call tokenization. So tokenization is very important in the sense that when you have in RAG, you would send you probably chunk a piece of your text, or you probably, let me say, you take a piece of your data that is mostly, let's say, a PDF. So those words in your PDF, you now take it, and then you when you take that word, those may be a sentence or maybe a paragraph. Now those paragraphs will now be chopped into smaller pieces, and those pieces are the ones that are going to now be converted into vectors that you now store inside your vector store. So if you go back to where we had, oh sorry, yeah, if you go back to where we had here, so you have your documents here, then you use an embedding model. So this is where the tokens are mostly created at. Then now those tokens are embedded. So embedding means that we now convert them into numbers, and then we now store those number representation inside a vector store. So that is what is very important. And that is why we need tokenization here. So that is what tokenization mostly do. And this is mostly the crucial step when it comes to NLP tags. So in our large language model, in our information retriever, because when you want to query your database, you send a prompt. That prompt is mostly converted into tokens, and then that is mostly what helps your models to be able to, or your LLM to be able to give you the response that you need. Now, let's understand types of tokens that we have. So we have word tokens. This is mostly split by spaces or characters. So for instance, if I say here that hello there, so hello there, here. Good. So here, what these word tokens will do is that it is going to split this based on what the spaces and the punctuation. So this hello will become a token on its own. There will become a token on its own, and then this exclamation mark will also become a token on its own. That is what the word tokens does. Then sub word tokens. What sub word tokens does is that it mostly converts the tokens into it mostly converts the token into subwords. So for instance, you have a word like, I gave you guys an example. So on happy, on happiness. Is that how you spell happiness? Okay. Yeah, I think it's S. Is it S? Is it E or I? Okay, one of them. So what the subword does is that it's going to first of all divide. Okay, when we get an implementation, I'll show you guys something. But mostly what this does is that it will break these words into mostly known words. Like UN is mostly a known word. Now HAP is also a known word. PI is also a known word. Then NESS is also a known word. So it is going to now split these tokens into these subwords. And I want you guys to know that all the LLMs that we have mostly make use of what subword tokens. Then we also have the character tokens where each of the characters in the word are split into individual tokens. So H here will be divided, E will be divided, will be a token on its own, L will be a token on its own, another L will be a token on its own, or be a token on its own, and all of them are going to be tokens on their own. The next part is the byte tokens. So the byte tokens, mostly what that does is that it converts the letters into binary units. Like I don't know if you guys know about UTF. Is it UTF-8? Yeah, I think UTF-8, and then ASCII characters and all of those things. So it is now going to take the numbers, the words that they give it to it, and then break them down into binary units. That is mostly what the byte tokens do. So we need to understand that another thing that I would like you guys to know is this. When ChatGPT came, I don't know if you guys remember this, somewhere in 2022, if you give it numbers, if you give it like maybe some maths to do, you ask it, okay, so in a bracket, 2 times 3 um, plus uh, 4 divided by 2, it is going to mostly find it difficult to do this for you because it is not able to, it wasn't trained to be able to recognize numbers. So mostly tokenizing numbers are mostly a tricky thing. Why? Because numbers could be large numbers, it could also be decimals. And because of this, mostly the LLMs or the tokens, the LLMs generate token text. They mostly see them as text instead of making them instead of knowing that these are numbers. So because of this, a hybrid approach is needed to be able to do that tokenization. So um, some of them could be, some of the LLMs use the character level tokenization, where they break these letters into individual tokens. And then we could also have subword tokenization, where they break the numbers down into their subwords. Like for instance, 2023 could be broken down into 20 and then 23. Now, the ones that are mostly used presently is the semantic tagging, where the numbers are given, we assign, if it is a date, we assign it a date. If it is a percentage, we are assigning it this. So these are called metadata, and these are tags that are mostly assigned to the letters. So this is how LLM process some of the numbers to be able to understand numbers. So one of the tools that is mostly used is Spacey. Those of you, I think, yeah, this is a Python package. If you are confident with NLP applications, you mostly might have come across this. We also have sentence piece, which we'll talk about, and then some transformers can also recognize numeric patterns. So, sorry. Okay, so tokenizations are important. I
Sorry,
talk
come
about the
on,
fact that we need them.
come on, can you hear me?
Yeah, yeah, I can hear you.
Okay, we're halfway through the session. I just wanted to let you know.
Okay, okay, yeah, thank you.
Yeah.
So, yeah, so we need them for text embedding. In RAG, we also, I think I've talked about this for semantic search and the rest. I think I've talked about this. I've talked about document chunking and the rest. So, um, LLMs, tokenization, sorry, is the heart of most LLMs, because for them to be able to spell words correctly, they need a tokenization. For them to be able to do simple arithmetic, they need tokenization. Mostly when an LLM meets this, what happens is that they will stop generating the response for you. I don't really want to bore you guys with most of this stuff, because I just want you guys to know about some of these things. Now, let's do some demo. You can scan this, or let me send this to let me share this. Please, I hope you guys can still see my screen, by the way.
Yes, we.
Yes, we
Okay,
can.
so we get back here, and then, okay, so here, yeah. So please, yeah, this is, I've sent the notebook. You can follow along. So let's talk about tokenization. So here we just installed a scented piece, tokenize. Okay, yeah, it's now connected. So we import a tokenizer. So we are going to be using the word tokenizer from NLTK. This is just a natural language toolkit. So, oh, connect. Okay, so this is just going to install. Then we load the token. We download the tokenizer, and then we apply the word tokens here. So if you take a test like welcome to nsk.ai rag, so here it is going to divide, it's going to break them down into the space in between them. It's going to break them down into that space. So here, welcome is a token on its own. Two is a token on its own. nsk.ai is a token on its own. And this is what we call the word tokenization. Then the sub word tokenization, we just load a sentence piece here. What's I don't really want us to worry much about this because this is mostly done by the LLMs. They are going to train their own sentence piece tokenizers and all of those things. But I just want you guys to look at the output here. So welcome to nsk.ai. So here, welcome to NSK. You can see that the NSK is now divided. It now breaks the NSK into individual tokens. So NSK and then .ai. So this becomes a token on its own. This also becomes a token on its own. So this is the subword tokenizers. Then the character tokenization is just about what I said. So well, WI, all of them are now sent into their individual tokens. Then by tokenization, so we have a text like Ghana, and then we want to encode this as what a UTF-8. So here, this is the numerical, that is the binary representation of the G, the H, the A, the N, and then what's the A. So this is byte tokenization. Now, in tokenizing numbers, this I don't really, I just show you guys the traditional way is just we having this, and then we now break it down into this. But then LLMs are mostly going to change this, mostly trained to be able to recognize that this is a year. So they will use this year token to represent it. And then this is a number. So they are going to use this num token to represent that. So this is tokenization. Let's quickly go through the next one. Yeah. So the next thing we're going to be talking about is neural networks. So neural networks were just modeled they're mostly inspired by the human brain. Let me show you guys something here. I don't know, those of you come from the biology background, you would probably might have come across neurons before. So a neuron is made up of this side, and then this side. So these are mostly called dendrites. So these are mostly called dendrites. And then so these dendrites receive what we call inputs. So inputs, this is also an input, this also an input. And then this is output. So this is what inspired neural networks, where you have input layers and then you have hidden layers. So the hidden layers are just the body of the neuron. So the neuron is made up of dendrites, and then this is the processing end. So this side is the input, like here, and then the body is the hidden layer, and then the output is what the neurons give out. So this is the body of a neuron, and this is how neural networks were brought into being. So they were inspired by the human brain. So that is what I want you guys to get it. Now, the neural networks are mostly made up of input layers. So they mostly take the raw or a formatted data. This could be pixels, that is the picture data, or text. Then we have the hidden layer, which I showed you guys behind here. So these are the hidden layers. So mostly these parts of the neuron. So they mostly extract the patterns. They mostly learn the patterns that are inside the data. They learn the weight, they learn the activation functions and all of those things. And then it also made up of, it also have the output layer, which mostly produces the results or the predictions that we want. Then we have the types of neural networks. So we have the feed-forward neural networks. This one, you have your neurons inside, and then what happens is that data flows in just one direction. There is no back propagation. Data flows in just one direction. So that is mostly what feed-forwards are. I guess feed-forwards are just like, I don't know if you guys, when you were growing up, your parents tell that you listen in this year and then it will just pass through that year. So you don't, that is mostly what happens. The data just goes through and then just goes out. That is neural networks. Now, convolutional neural networks, that is CNNs, are mostly designed to handle large data, to process image data, and they mostly form the foundation of basic computer vision applications like image recognitions and the rest. Then we have the recurrent neural networks. They are mostly designed to process sequential data like text, like maybe a time series data and all of those things. LSTM, that is long short-term memory models, are one of them. Then we have the transformer models, which we are going to go deep. We are going to dive deeper into this one soon. So let's also do some demo to illustrate to you guys how neural networks work. So here in the notebook, we have, I'm using TensorFlow here. So using the Keras API. So yes, import this, and then using the handwritten digits. This mostly comes to the Keras API. So we download this, and we want to be able to recognize handwritings. So we just want to view the first. So this is 5, this is 0, this is 4. So we are going to be training the model using this to be able to recognize a handwritten number. So if you view the 17 value, this is 8. And then I want you guys to understand something, that the values, where the 8 is dark at, where there is these things that you guys are seeing, these boxes are seeing, are mostly called pixels. And then the darker the pixel, the higher the pixel value. So if you should print this out, oh, sorry, I wasn't running this. Oh boy, I hope this doesn't take time. Okay, so if you should, yeah, load this and then run this. So if you should take the 8 out, I want you guys to look at the 8, how it looks like. And if you should run this, so just look at the portion of the 8. So where the dark circle, the dark pixels are having the highest value. So that is what these are the values that we are going to feed into the neural network. Now we just normalize the images here, and then we create our sequential model. So here we just flatten the images just to put them into just to have like a long value. I don't want you guys to worry much about this. And then we have a dense neural network, and then a dense neuron, so with 128 neurons, and then this 10 is just to represent the number of outputs. So we have from 0 to 9, which is 10. So we run this, and then we compile this, and then we train our model by giving it the training data, and then we give it a training data. We set our validation to it should validate the model on just 10% of the training data set. So this runs, and then I don't want you guys to worry much about the training loss and all of those things. I just want you guys to understand how neural networks are. So this is how they work. Yeah. Okay, so I think this is okay. Now let's go quickly to transformers, and then we should how am I doing time wise?
You're good, you're good, you're good. You're good.
Okay, great.
Take your time.
Okay, yeah, okay, thank you. So let's talk about transformers. So a transformer model. This was actually introduced in Attention is All You Need. This book that was written, this research work that was written by Google, some people from Google. And it was initially designed for translation of text, so from one language to another. So they are mostly an advanced neural network architecture that is mostly designed to handle sequential data, so especially text data, to be able to translate one language into another language. And what happens is that they process text, the data that we are going to give to it, they process that text in parallel, meaning that they don't, in RNNs, we didn't talk much about this. Oh, sorry. We didn't talk much about this, but RNN mostly process the text from one sequence, from one value to another. But here, they process the text in parallel. So and the total number of words or the total number of sentences or whatsoever it is, they process all of them together at the same time. So that is mostly that is a strength. And then the user attention mechanism, which I'm going to talk about, and they mostly power modern GPTs and then the rest that we have. Now, let's talk about the transformer architecture. So the transformer architecture has the input embedding. So here, this is mostly what receives the input data. So you have maybe a set of your words. So it receives those words and then it now converts them into embeddings, into tokens. So we split them into tokens. They will now convert those tokens into embeddings, that is vectors. So we now vectorize those words. That is mostly what the input embedding does. Then the multi-head attention. This is the most important aspect of transformer models because now we human beings understand this. So let me say this. Let me give you guys this example. So if I say I consume, I hope that's how we spell consume, Apple products. Okay, so I consume Apple products. Now here, you human beings will probably know that this apple I'm talking about is not the fruit apple, but what a company apple. So what the transformer models mostly do in the multi-head attention, it is able to give particular attention to a particular word, given the context. So let me also give you guys on that how mostly this is mostly done. So let's erase this. So let's say I ask, we have this text. So install Python. So let me just give this example. Install Python on your PC. So I'm just going to use I here to represent install, then Python P, then on here. Oh, sorry, I'm writing inside this. Then Y for your, and then PC. Let me just use a PC this. So here, install Python on your PC. The most important, if we ask ourselves, what are we installing? Okay, so we are installing Python. Okay, on our PC, right? So the on and PC most don't really play much when like they don't have much weight when it comes to this sentence. So what the multi-head attention do is this is going to assign weight to the particular relationship in the words. So install probably maybe it's going to give maybe I'm just going to assign some value. So let's say 15%. Install Python. Okay, so we are installing Python. So that makes sense. So it means that it's going to assign
I got my yesterday. We only like we lost you. Oh, we sorry about that, guys. Let's walk.
sorry. Please, am I audible now? I think I just got
Yeah,
frozen.
yeah, we lost you for
Okay, yeah.
like a minute.
How many
Yeah,
minutes?
can you share your screen
Okay.
again?
Yeah, okay.
Thank
So reading, share this. Is it showing now?
you. It's coming up. Yeah, it's off now. Thank you.
Okay, yeah. Sorry, yeah. Okay, so let me share this again. Yeah, so I was talking about this. Go back, go back, go back. So here we have install. So let me just use install Python on your PC. So we have install Python on your PC. So here I was talking about we maybe give it like 10%. This will assign 50% to this because um, install Python. So it means that it knows that Python plays a huge important role to this word install. That is why it is going to probably assign 50%. And on your PC, so maybe this is going to be like 5%, this is going to be like 5%, and this is going to be like, let's say 20%. So on install PC, okay, so install has a huge, so if you look at this, the relationship between install and these words, okay, and these words, these values now becomes what we call the attention matrix. So this attention matrix is able to let us understand that, okay, it tells us the relationship between this word and then the other words that are inside that sentence. So that is mostly what a multi-head attention does. It's able to learn the different types of relationship that is in the words. And then that relationship is now passed on to the feed-forward network, which mostly performs the transformations. So maybe we want to process a text, we want to maybe generate a text. So that is mostly what a feed-forward network does. Then the layer normalization is just to help to stabilize the training, in the sense that these values that we have here, they need to be normalized so that because when we have higher values in the machine learning, mostly the machine learning algorithm mostly tend to give it more attention. So we normalize those values to be within a particular range. So that is what the layer normalizations do. Now we have type of transformers. We have the encoder only transformer. Mostly this encoder only transformers mostly utilize the encoder component. Sorry, the encoder component. And these are mostly important for effective in taxes like when they want to mostly deep understanding of the way of the text that you are of the of the response. So they look at this, the encoder only mostly looks at the words critically, like it dives deep into them to be able to understand the nuances in them, to be able to give the output. So I just want you guys to think about the encoder only models, like you knowing maths, like they give you a math question. For you to be able to solve, you need to understand the formulas. So that is mostly what encoder models mostly are made up of. I don't want to dive into the deep technical aspects. Decoder only models are most like the GPTs, most of the LLMs that we have currently, and they mostly generate the text. They mostly generate text output, and without they generate, they predict the sequences in the text. So, like, also without really going into the technical details, I want you guys to think of it like you are given an essay to write. So I am happy to write you this letter. Okay. So the reason why you put happy before I'm happy before I am is because you are predicting the next words. So that is mostly what decoder only models do. They are mostly good for generating text. Then we have the encoder and the decoder models, which are mostly for the neural translations, like models like the T5 and the rest. So here they have both the encoder and the decoder models together. So that is mostly what the types of transformers that we have. Now, how decoder models work. So what they do, what happens here is that you have this here is mostly considered as the context vector. And then this context vector, which is mostly done by the encoder model, is passed on to the decoder. Now, for this decoder to be able to predict, initially we have this token called the start of sentence token. So for this decoder to be able to predict the words, what is going to do is that it's going to learn the relationship between this I that it wants to predict, that is going to predict. It's going to look at the relations that this I have with all the tokens that are inside this encoder, the output of the encoder. And this process goes on and on and on and on and on and on before you are able to get all the words fixed together. So like I said, I just want you guys to understand this in this high abstract level, not to bore you guys with the technical details about this. So let's do some demo on encoders on the transformer model. So here, I didn't want to cheat those of you who are conversant with PyTorch. So I did the neural networks in what's the name, in Keras. So let's do the transformers in PyTorch. And mostly like transformers in PyTorch are mostly most easy to do because I don't know, I've never really done that in Keras before though. So here we import our libraries and then we have some piece of text and we build our vocabulary. So what we want to do is that this is where we are going to now convert, put out of all of the texts together. So that is mostly what we do. When you put all the texts together, what you are doing is that you are building a vocabulary. This is mostly what they do to train all the LLMs that we have today. Then we encode those vocabularies into their character indexes. This is where we are now converting them from letters to numbers. Then we build a simple transformer model. Here I just want us to we are just doing an what's the name, an encoder mode, just an encoder only. So we have our embedding layer, which is going to now which is now going to put all the numbers that all the letters that we are bringing to it into a numerical representation, and then we give it a position embedding. We have in PyTorch we have this transformer encoder layer, which mostly handles all the encodings and all of the things for us. This is just a simple, and then these are feed forward. This is just a simple model that I want us to just look at. Don't really worry much about the outputs because we've not really trained this much on large data sets and all of those things. So we initialize our data model and then we give it a text. So this is the prompt that we are giving to it, and then this is the result it's giving to us. This is not making sense, but this is how large language models came about. This is mostly how large language models came into being. So these just like some further improvements that I want us to look at. Give it some parameters to be able to check whether it's going to give us some interesting output. So we are training, in mostly production ready transformers, you'd have huge parameters. You have so many parameters, and then you have so this one I'm just using this to be able to give us some fair idea of how these large language models are. So we are training this, and then we give it a sample prompt. And then here, this is the prompt I'll give it to it, and this is the output. So this just generating some set of text for us. And this is how transformer models work. This is how transformer models work. So that is transformer models. And that is what I wanted you guys to get. So now let's look at some key takeaways. So we talk about AI models. Oh, sorry. We talk about AI models, which are just mathematical tools that learn from data and help decision making. We talk about tokens, which are units of text data that the computer uses to be able to understand natural languages. We also about neural networks, which mostly works like the neurons in our brain. They take an input and then they process it and then they give it an output. So that is it. Then we also have transformer models, which form the basis of today's LLMs. And then all of these things are very important in RAG applications because they are all the pieces that we need to put together anytime you want to develop a RAG application. So this is where we bring the curtains at. So it's Q&A time. If you guys have questions for me, you can ask, and then yeah, so questions.
Thank you so much,
Right.
Omar. Thank you so much. So I think this is the Q&A session. If anyone has questions, you could put in the chat so we can ask. I'm sure many people have lots of questions. There was a question I saw. Let me see.
Okay, I think
Emmanuel
I don't
has
get
a
a vector
question.
store. I don't get a vector store. Are they databases? Okay, yeah. So back to vector store. In RAG applications, okay, you need a vector. Okay, let me in a RAG application, okay, you need a vector store. So here it's just like, is okay, let me say it's like a database though. So what happens is that you have your words there, you have maybe a PDF file, and then you want to be able to query that PDF file to be able to give you some information. Now what you do is that you now take that PDF, and then the words that are in that PDF, you create a vector of them. A vector meaning that each of the words that are in that PDF, you now convert them into letters. Now into numbers. Those numbers are now kept inside the vector store, just like you are saying. Are they like a database? Yes, they're like the database. So you keep them there, and then you now go to query. Whenever you send your prompt, the prompt goes into that vector store to query the values inside that vector store to now give you the retrieve information. So that is what vector stores are. I hope that answers your question. The name again, Emmanuel. Yeah, I hope I pronounced. Okay, thank you, clear. Thank you, Sai, for
Okay.
answering most of the
Yeah,
questions.
there's
When fine-tuning LLM
okay.
models, please.
Gamma, there's another question. Okay. Okay.
Yeah.
Yeah, that's
Yeah.
it. That's it.
What's the difference between word token and sub token? Okay, so word token, let me go back to the slide. Word token, okay, yeah, so word token, like I said from the beginning, you have here, okay, so let me use these examples. You have we love NLP. So what happens is that the we, it's going to separate it based on what the space. So we love NLP, then the question, sorry, the exclamation mark is also going to be what is going to be put into its own token. But for the sorry, the question again, is it character token? Where is it? Where is it? Where is it? Yeah, and a subword token. Okay, so the subword token, instead of um dividing this into words, what it does is that if you have a word like unhappy, I think I gave an example of unhappiness. So unhappiness. What it is going to do, what a subword is going to do is that it's now going to divide, it's now going to break these words down into various tokens. So this one word can have what you can say we have 1, 2, 3, 4 tokens. So UN will be a token on its own. HAP will also be a token on its own. Then P or pi will be a token on its own, and then the NES will also be a token on its own. So this is the subword tokenization. So that is the difference. I hope that answers your question. Simret, I don't know if that's the name, the word, the Spanish. Sorry if I'm murdering people's name today. What do parameters? Yeah, please let me know if that answers your question so that I will move on to the next question. Okay. What do parameters mean in context of LLMs? Okay, I usually hear something like, for example, GPT have trillion parameters. Okay, so parameters in LLMs are they are debatable concepts. Okay, um, parameters could be in terms of the training parameters. So that is one parameter. Another parameter could also be in terms of the amount of data that was used. So there are so many things about parameters that if you want to look at it, if you want to dive deeper into that, it's mostly a thing of um how should I put it? A thing of the engineers that are working on the thing. So it could be the number of, like what I showed you guys in the notebook here. Okay, sorry.
Yeah, I can briefly also add
Yeah,
to
please.
what Gama mentioned.
Yeah.
So it's just like
Okay.
number of numbers basically used in these models. Number and they you can also consider them as like the number of neurons as well. And if GPT says they have trillion parameters, it means they have trillion integers or floating point numbers used in that model. So you have that many number of multiplications, additions happening.
Yeah. Great. Thank you so much.
And
What's the
there is
crowd
one
just like?
question
There's
in the
another
there's one
Please,
question
can
in
I
the
slide
Q&A.
you
QA
said
section.
yes? Okay.
Yeah,
Yeah,
in the
Gama.
Q&A
Q&A
section.
You,
section.
yeah.
Okay, where is Q&A?
So go to
I
more.
can read the question. So
Yeah,
it
please read the
says,
Okay,
question. I
fine.
can't.
yeah, when fine-tuning or customizing LLMs for agent behavior, how do you balance between prompt engineering, few-shot learning, and actual parameter fine-tuning? And how do you measure
Okay.
which one is giving better control?
Okay.
Uh,
Sorry, okay. I didn't catch the question though.
I'll post this. I'll copy paste this in the chat
Okay.
itself. Yeah.
Okay.
So
Yeah.
I can take a shot at the question. Gamma, jump in as well. Uh,
Yeah, you
so
can go
it
ahead.
it it depends on what type of data you have. Like of course, fine tuning the model is better to improve the performance, but usually we don't have as many training data, or we might not have the ability to fine tune the model. For example, we won't be able to access GPT-4 for easily fine tuning. At that time, prompt engineering and few short examples are the one that we can use. And it also depends on what type of task you are dealing with. If it's a really complex task and if the current model is not at all able to do it, then we have to use fine tuning. But yeah, I mean, like if it depends on if you have them access to the model. Most of the big companies use all three of them. But since we don't have access to these models, we probably should start with prompt engineering and few short examples, not few short learning, few short examples. Uh, yeah,
Yeah.
feel free to add to that answer.
Yeah. I think you've done that. You've done justice to that. So just like you said, fine tuning, parameter fine tuning. Mostly, I think that's mostly what the model developers can do that, because I'm not sure you are going to have access to the models, or unless maybe you develop your own models. Yeah, but we what you said, prompt engineering, and then the few shots. No, you not like few shot learning. You giving examples to your parameter. So you give examples, sorry, your agent to be able to learn from those examples. I think that is going to give you a better result or a better control. So thank you, Sai, for that. Yeah. Any other questions? Any other questions that I missed? Because honestly, I think I only saw the only question I saw in the chat. Okay, yeah, I think I've seen it now. Yeah, sure.
And if any, can you answer there are a lot of questions about slides being available. Can you answer that?
Oh
And
yes.
recordings.
Okay. So we're going to. So I think in the mail we're going to
Sorry, can
send.
I
We have this
can I
code.
stop sharing and then can I just stop sharing? Or
Yeah.
okay.
So we should send the slides will be shared in the mail that we'll share today. Yeah. So we're going to send that tonight. Tonight, I guarantee to everyone. So I guess we're done with the questions. Gamma, I'd like to say a big thank you to you. Um, it was really a fantastic talk. I learned so much. It's really amazing how, being in this AI era, you think you've been here for a while, but you still learn things every day. So Gamma, I must applaud you, and I think everyone on the call learns a lot. For some people, I know it might feel like it was a bit complex, but there was a lot he said. So do take your time to watch the video. The link to the video will be made available to everyone today. Tomorrow I will be having a talk tomorrow, so we'll be touching on a research paper, um, RAG for large language model. So we'll do like a survey of how like RAG has progressed from the beginning, like the first type of RAG to naive RAG to mid RAG to advanced RAG. So we'll run through the entire history. So it's going to be a technical paper talk, and it's going to be really exciting. So same time tomorrow. Um, we know that there have been issues with people not receiving emails or not having Teams. We're going to get a form ready for you in the mail. We'll send it and put it on the Discord and the WhatsApp. So everyone can, if you're having issues with your emails, you fill that form. Yeah, thank you, sir. If you're having any issues, there's going to be a form for you. So we're going to address all issues, and all emails are going to be sent out today. Thank you all. One reminder once again, please, the bootcamp is still open. So if the people that want to join, it's still open to your friends. And yeah, thank you all once again, and you have a lovely night. Okay, goodbye, everyone. Bye.
Bye, guys.